Yes. So, like I said, it seems overwhelming, but my hope is that when you get into doing these quantum mechanical calculations in Excel, the light will come on and you'll be like, oh, this isn't as confusing as I thought. And we just have these waves, you make them in Excel and then you plot them and you're like, okay, there they are. Take the first derivative, not a problem. Take the second derivative, also not a problem. Multiply them by each other and integrate, and you get some constants out front that are useful. Yeah. So this is the numerical approach to the Schrodinger equation and all those transition dipole moment integrals and everything. And so why use numerical methods of calculus? Well, Dirac was saying that we know all of the equations um, for chemistry, but the solutions are too difficult. And in fact, we actually some of them don't have solutions, like our 2-electron systems or multiple electron systems. We have not figured out an exact way to solve for what they call electron correlation. So in the Hamiltonian, you have that V piece that we haven't talked about. It's the potential energy function piece. And we'll get into that with Gaussian. But we're not able to model the repulsion of an electron to an electron because they're behaving as waves. Now, what does the Coulombic repulsion equation require? In the denominator is the distance between the two particles. If I've got a charged particle and a charged particle, they repel each other if they're the same charge. And the strength of that repulsion is dependent upon the distance. So if they're really close, there's a huge repulsion, and if they're really far, there's very little repulsion. But that distance between the particles is a key piece to that Coulombic repulsion or attraction if it's to the nucleus. But we're dealing with electrons that are waves. So there's not a single location for an electron. So I can't calculate that repulsion piece. So that's electron correlation, and it's a piece that we don't have an answer to. So then numerical methods utilize fast computation of complex problems, and so this is why we're using them. So this is walking through the small spreadsheet project that you have that's in the next week's folder, that blank XLS form that you're going to go through. So it's the one you have is blank here. So these wave functions down here are not filled out. So you're going to start out and it's empty right here. So you're going to use your your Excel bootcamp skills, and you're going to put in the wave functions. And what is the wave function? Well, it's this function right here. So you're going to learn how to put this function into Excel. Okay, and you're going to anchor it to these quantum numbers up here. So these are n, right? N and n prime. And so you're going to anchor those, and you're going to have this, n squared. So this is, just equal to this one squared. And so you square the wave function. So that's that probability distribution for wave function n. Here's wave function n times wave function n prime. The nice thing is it's dynamic. So if you change these quantum numbers after you get all of these in, then the waves all change. And we did that last time. I made it like equal to 9, and we saw some funny business with the wave functions. But here we have it. So this is n equals 2, n prime equals 3. We see that over here. Yeah, see here's n, and here's n prime as we've got them labeled. If we square those, notice that the blue wave function had some negative pieces. Okay, it had a positive piece and a negative piece. When we square it, that's now positive on both sides. So that's the probability distribution. Quickly, let's just analyze this. What's the probability of the electron being in the very center of the box? Yeah, 0, because it goes right here. It's going through 0 right there. So that's a quantum effect, right? Why wouldn't the electron be in the middle of the box? That's just the box. It can be anywhere. Why wouldn't it be in the middle? Well, because in the n equals 2 state, it's oscillating like this. If we square that wave function, we get the probability distribution, and it's not in the middle of the box in the n equals 2 state. Why? Well, it's because it's behaving like a standing wave. That's a quantum effect. Okay. Now this orange curve here is just curve 2 times curve 3. So wave function 2 times wave function 3. And it's not a square. It's two wave functions times each other. And so it's got a positive piece, it's got a negative piece, it's got a positive piece, and a negative piece. And if I integrate that over all space, can you see that all the positives and negatives are equal and opposite, and it's going to end up 0? And so we would expect that the integral of this is equal to 0. Yeah. And the integral of this one is equal to 1. And so that's what we do here. We use sum product to integrate n squared. We use m mult to integrate. And so 2 times itself is 1. 3 times itself is 1. 2 times 3 integrated over all space is 0. 3 times 2 integrated over all space is 0. So we can see the Kronecker delta in this matrix. You could write out this matrix, or you could write out that delta n prime, where it's equal to 1 if n equals n prime, and it's equal to 0 in all other cases where n does not equal n prime. So yeah. So and down, I don't know if that's one of the discussion questions, but it's just the question here. You can say yes. Yes, no question. Also looking at the symmetry of the wave functions, even and odd. We haven't really defined that. If I have a function here, let's look at the blue curve. And if I go to the right, say to 0.1, like if I go to 1 unit in the positive direction on x, and I evaluate that function, I get minus 0.4. Does everybody agree with that? Here's minus 0.4. Yes? Okay. If I go the same distance in the other direction to minus 1 and evaluate the function, I get plus 0.4. So they're equal in magnitude, but opposite in sign. Do you understand the language? Equal in magnitude, they're both 0.4, but they're opposite in sign. That's the definition of an odd function. So by definition, that's an odd function. When they're equal, you go in the same direction, they're equal in magnitude, but opposite in sign. So that's an odd function. And down here, we have that the symmetry of these wave functions, n equals 2, is odd. What about wave function number 3? Let's erase all that mess. Let's just go forward 2, because 1 is real close to 0. So we'll go forward 2 and evaluate the function. And I get positive 0.5. And I go left 2 and evaluate the function, and I get positive 0.5. So these are equal in magnitude, same sign. That's an even function by definition. So we can see that this is even. Now we have certain multiplication rules too. So an even function times an even function gives an even result. So let me go ahead and label this blue one O for odd, or O even. Okay. And then what if we had an odd times an odd function? It'd be even. You can think of these multiplications of even and odd not like even numbers, like divisible by 2. What we're talking about here is more like plus 1 and minus 1. So think about even being plus 1s and odds being minus 1s. So if I have 2 minus 1s times each other, they become plus 1. Okay, so this is an even here. And then if I had an even times an odd, what do I get? Well, I have an even represented by a plus 1, odd represented by minus 1. What's the result? Minus 1 odd, yeah. So that'll be odd. So here we have this n psi of n squared here. We have an odd function times an odd function. It should be even, and it is. We can see here this psi 2, 3. This, let's see. No, that's this blue one. This was blue, 2 was odd, so when we multiplied 2 by 2, we ended up with an even function. You see how it's even? It's the same on both sides. Same sign, same magnitude. And then 2 times 3, we have an even times an odd, and we get an odd function. Same magnitude, but opposite sign. And so we see that over here too. in your spreadsheet. So that's panel one. That's just working with the wave functions, checking to see if they're normalized and orthogonal. Okay. So you guys can do that. You enter the formulas, play around with it, and there's some discussion questions below this. And then you have your quiz that quizzes you on this. So it's all about this next week, for getting ready for that quiz. Okay, let's go to the next panel. Okay, this is all about arrays, that matrix multiplication. This is in the boot camp, so I'm just going to breeze through it. You have the columns and the rows, and we always refer to matrices as row first, row by column. Okay, and then we learn by inspection. The transpose flips these things. So we transpose things with that diagonal elements are A and E, so we flip them on that diagonal. Okay. And then notice that anytime we have vector multiplication or dot products, we end up with the sum. And so that sum can represent an integral. And so this is expanded with matrix multiplication. So we have M mult, array 1, array 2. The trick is you've got to select a certain area. So that's where the row column requirements come into. So this matrix multiplication rule, you have to know this because you have to select the right size panel. Okay. Now we're going to have 15 wave functions in our big project by 100 rows. So that's a 15 by 100 piece. And then we're going to transpose that and multiply it by that. So we got a 15 by 100 multiplied by a 100 by 15. Okay. And so the end result is going to be the outer numbers. So 15 by 100, 15 is the outer number, multiplied by 100 by 15, 15 is the other outer number. So we're going to select a square of 15 by 15. And then we're going to type in equals M mult, open parentheses, then we're going to go select, we're going to type in transpose and then select that block of wave functions, comma, go select that block of wave functions again, close parenthesis, times delta x, so we get, so it's an integral, times delta x, and then we have to hit Control Shift Enter to make it go. Now, I don't know how to do that on a Mac. Do you know? Does anybody use Mac? Is it Control? Okay. Okay. Okay, very good. Okay. Yeah. 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 Okay. Very cool. Yeah. So you have to select that n by n matrix. So in our situation, we have two wave functions. And so when we transpose it, it flips it up to a 2 by 10 or 11, and we're multiplying by an 11 by 2. And so we should select a 2 by 2, type in the formula, and that's what we're doing up here. So this is in that spreadsheet, you're using the matrix multiplication on a 2 by 2 instead of 15 by 100. I originally had done this with the big spreadsheet for all the students, and they were just so lost because it was so big. And so I made this little mini version. So I want y'all to go through the mini version before you do your big project. Yeah. Okay. And then you can see that orthonormality. Okay, so then then the second piece. Then we solve the Schrodinger equation. So we have our wave functions. We have to enter them again because I have a whole nother panel here. So we enter those wave functions again, but now we expand the box. So our box is, it really goes from here to here. Oh, shoot. Go back. There's little tools on Excel that are screwing me up. Yeah, so this is the box here in the middle. I put a big black box around it because this is, our box length is 7. Well, no, it's 3.75. I don't know what that is. 6.75. Okay. Yeah, so, but anyway, this is minus L over 2. And this is plus L over 2. Why am I writing 7 over 2? That's ugly. Let me fix that. Top one is minus. But we had to expand it, and we're going to talk about that here in a sec, to get the center derivatives. And every time we take a derivative, we lose a row. So we lose these first two data points when we take the derivative, and we lose those two data points when we take the derivative again. So we've got psi double prime of n, psi double prime of n prime, and here's our psi n and our n prime. We have these constants that we have to put out front, and so we have to have those defined up here. So we've got our constants, we've got particular units on those. Our box length is angstroms, and so we've put in there the conversion factor that there's like a 10 to the 20 angstroms squared per meter squared. So that's where 20 orders of magnitude went. And so now we've got, instead of Planck's constant in meters per second, meters squared per second, we have it in angstroms squared per second. Okay. We also have it in kilojoules, Planck's constant in kilojoules seconds, instead of joules. And then we've got Avogadro's number. So we've got all those constants in there. We use one Planck's constant, CH squared. We use one to cancel the angstroms, and we use the other to give us kilojoules. So instead of Planck's constant squared, we're using Planck's constant with two different units. It's still Planck's constant, but it's in different units. So that's a little tricky thing. Then we've got the mass of the particle defined over there. That's the, so you refer to that spot. You got pi. If you want to use pi in Excel, just do pi open close parenthesis. And it's a function that pulls in pi to like a gazillion decimal places. So you don't have to type in 3.14, just use pi open close. Nothing in the middle of the parentheses. Okay, and it'll pull pi into that equation. And so when you do that, you can do it by sum product. So you can take all these constants times the sum product of the wave function here times its second derivative, and add them all together times dx, and you get that number right there. So you could do the energy levels individually by taking the wave function and times its second derivative and all those constants out front, and you get that. You could also do it using the M-mult. So I have you do it both ways just so that you're good at doing both of them. Okay. Now this in analytical energy, that equation is your regular analytical result. So that's h squared n squared over 8ml squared. Okay. There's no wave functions or anything like that. That's the analytical result of the Schrodinger equation, and so that goes in here. Notice for our particular energies, we've got 12% error on this one and 26% error on that one. And that's just because we're in an excited state, and we're doing it numerically, and we're only dividing our box into 10 units. Okay. So that's the Schrodinger equation. We have the energies. Okay, doing it at high definition, we could do 15 by 15. Okay, but here it's the same. This is the matrix multiplication for the Schrodinger equation. Here, instead of doing the wave functions times themselves, we have the wave functions here. I've transposed them like that, and then times the second derivatives. And we're only selecting the blue values. We're not using those extra ones. So we're only selecting those, the 2 by 11 matrix multiplied by the 11 by 2 matrix. And we get this 2 by 2 matrix. So those are the energies. And then we do the third piece, solve for the selection rules. So now we want to see if the transition from, say, in this case, 2 to 3 is allowed. So we have two quantum states, n equals 2 and n equals 3. We've got the wave functions, and then we have light. So light's coming in and perturbing that wave function. So we have the x-axis times the wave function to give us this column. Okay. And we can see what that's done. Here's our wave function. Let's look at the wave function number 3. Okay. So the x-axis, if I have f of x equals x, it's a diagonal line like this. Would you agree with that? This is f of x equals x, if you were to plot that. what is it in negative x, right? It's going to be in negative numbers. So I have negative numbers times positive numbers, and I get this shape right here. See, it's negative. And here I've got negative numbers times negative numbers, and it's positive. You see how it's working? And then over here I've got positive numbers times negative numbers, and the result is negative. And here I have positive numbers times positive, so it's even taller. Okay. So light has perturbed that wave function. It has changed it. It was an even function, and now it's an odd function because x, the function x, is odd. So I took an odd times an even, and I ended up with an odd result. So light comes in, it changes the symmetries of the wave functions, and it's going to change the integrals and all of that. So we can look at the selection rule. We can calculate that integral here. How do we calculate it? Well, we've got the wave function times x times the wave function times dx, okay, and add it all together. So that's a sum product. So this is the sum product of psi times x psi times dx. We could also do that in matrix form, okay, where we get all the possible transitions. So we can go, if, there's no 2 to 2, the result is 0, but 2 to 3, the result is non-zero. And then 3 to 2 is non-zero, and it's equal to the other. So it doesn't matter which one you do first, obviously. And then 3 to 3 is 0. So we get all of those possibilities. Can you see the selection rules, even in a 2 by 2 situation, that delta n can't be 0, because I would like delta n can't happen because the result is 0, at least for light. There's no absorption if the molecule doesn't change its state, right? So it kind of makes sense. But 2 to 3 is non-zero, so a delta n of 1 is allowed. You can play with these numbers and come up with other selection rules. Like you could put 1 in there and you could put 3 in there and see if a delta n of 2 is allowed, and you'll see that it's not. You can put 1 in there and 4 to see if a delta n of 3 is allowed, and it is. So you can play around with this on an individual basis, but in your big project, you'll have 15 by 15, and you'll see all kinds of ones. So this is what we did. Here's what you'll see. If you have the same box length as I had, this is actually for a 200 angstrom box. You see this as a result of this integral. So this is a 15 by 15 matrix that you guys are going to have. And you can see the selection rules here, this pattern. So 1 to 2 is allowed, and then 4 to 5 is allowed. 3 to 3 is not allowed. Okay, 6 to 6 not allowed. So integrals are 0 when delta n equals 0 or 2 or 4 or 6. Integrals are non-zero when delta n equals 1, 3, and 5. We saw this in our analytical results with the cosines. So we had cosines with some stuff in it, and when it was a delta n even, the cosines all went to 0. That was the analytical result. So we saw for the selection rules already using analytical calculus. We get the same selection rules using Excel, which is a good thing. This was a very exciting day when I said, I wonder if I could just do this in Excel. And I'm playing around on my computer, and think about how long it's taken me to talk about this. 40 minutes. It took me much longer to build the spreadsheet the first time, so several hours I'm into it. And I hit Control-Shift-Enter, and I get this 225 integrals, and I see the selection rules that I got from analytical calculus. That was phenomenal. That was so exciting. Yeah. So I saw this pattern. I saw that only odd changes in quantum numbers were allowed for 1 photon of light. The 1 photon of light comes in, and it can only make it jump by an odd number of quantum states. So 1, 3, 5 are all the non-zero ones. So we can have delta n plus or minus 1, or plus or minus 3, or 5, or 7, or 9, or 11, and so on. Okay. So those are the selection rules. So we're looking for the non-zero probabilities. And that's the definition of the selection rule. Is this peak allowed? It's kind of bizarre to think about it. Even though the light may have the right energy to cause a change in 2 quantum states, the wave functions won't let it happen. So it's forbidden for it to jump 2 in this particular situation. So then we get to the plot of the simulated spectrum of the transition. We do it for one peak here. So we've got to calculate the Boltzmann factor. It's the thermal population of that ground state, or the initial state, I should say. And then we've got some wavelengths. We've got calculations associated with the energy of the upper state, the energy of the lower state, the change in those two, so the difference between those two, and then converting it to wavelength. So follow your units and so on. This is the wavelength in nanometers. This is kilojoules per mole for the energy. So you've got to take into account Avogadro's number. Got to get out of kilojoules and all of that and into nanometers. And then we will plot that. So this has the Gaussian line shape intensity. And so here's your peak at 300 for the transition from 2 to 3. So this is lambda 2 to 3. How do I know that? Well, that's because that's what was in this spot right here. So in this spreadsheet, when you're solving for the selection rules, this 2 and 3 right here are the two wave functions that you're modeling that you're going to then plot the spectral transition for. So if you want to know where the 3 to 4 peak shows up, come over here and change 3 and 4, and then your peak will shift around. This peak will show up, where are we? Your peak will show up in a different spot at the 3 to 4 transition. Okay. So it's a little tedious. You go change the quantum numbers and come back and look at your peak. So let's not do that. Let's do the big project spreadsheet, and you get all of the peaks, which is this one. So your project will produce all of this, but it's using every little piece that you have in the small spreadsheet, only bigger, higher definition, and you can really then play around with the mass of the particle, you can play around with the box size, and you can see the whole spectrum shift around. So you will have gotten your hands greasy up to the elbows in the engine of spectroscopy. Okay. And so then once we're done with this, we're done doing it at this meticulous level. We'll let Gaussian do the work. So we'll close the hood. We'll put Gaussian in the hood space, close it, and let Gaussian drive our spectroscopy modeling. Okay. But you will have gotten, like I said, greasy in the process, and you'll hopefully have an appreciation for what Gaussian is doing. So I'm just worried because I know you're thinking, is the whole course going to be like this? It's not. We're going to get to practical applications right away. But I wanted you to dig through the engine first.